Well, now they're going to have to deal with how they keep us from hiring you. I mean, that's going to be up to you, I suppose. But
The guy,
that's my other
well, I got to see Rose, supported, so that was good. So I can check that rock, he was like out the other way. Glad they did end up.
yeah.
Yeah, we saw right from the library.
You do?
We're kind of coming to you.
With an A? I'd love to get him. But I would, at that time, I would get
The guy who knows the height. Yeah, I think people like really want that stuff.
We had 3 or more. That's how we made it great here. And we would
There are 2 students in the I don't think anybody give up.
So maybe that's
We go back here like
Yeah, so
feeling comfortable with your life.
running around everywhere.
Wait another minute or two.
Honest.
Is Dan, for one thing, I see getting cookies.
I did see a lot of dynamo today. So what? A lot of
Yeah, I mean, the amount of growth that happens in those first few years.
Okay. Out of the light. Hello, everybody. Thanks for being here today. So hopefully most of you saw the talk yesterday and a more extensive introduction. For this introduction, I wanted to mention that Chris has been a pioneer in running high-resolution models and gaining physical insight from them for quite some time. That's part of his history. And of course, the machine learning that he was describing yesterday trains on these high-resolution models as well. So that provides another reason to understand what they're good at and what they're not good at. And so that's what Chris is going to tell us about today.
Okay, thanks,
So-
Larissa. Yeah, so as Larissa said, high-resolution models were sort of my inspiration for going into machine learning because they just look so cool. And especially as someone who studies clouds, I look at an image like this. Wow, that really does look like something that's a model of the Earth that surely we should be able to learn something from. And so, really the question is, okay, there's cool visual impression, but as we know, cool visual impression doesn't necessarily mean a model is right. It just means it could trick your eye into being right. It's all about what machine learning is in the first place. And so the question is, to what extent are these models more right than models that we use? Or to what extent could they give us insight, especially insights about climate, but also extreme weather, that maybe we couldn't get from other kinds of models simply by virtue of their finer grid? So that's what I wanted to talk about today. I don't think this will actually be that long a talk, and so there should be plenty of time for questions afterwards if you have many. So I guess I wanted to mention that in my present time, the only way that I'm actually involved in this field is by trying to persuade people to do interesting simulations with high-resolution models, and in then editing the papers that they create, and they say, okay, well, you told me to do this, and it kind of works, and like, do you think this is actually worth publishing? So that's what I do, and so as a result, all of the work actually gets done by colleagues of mine. And most important are the colleagues at GFDL. So GFDL's very highest resolution models were actually created by a guy by the name of S.J. Lin, who has since gone to China, but who was sort of by himself, just a master model architect. He just loved developing models, and he was very good at it. But his apprentice in that was a former University of Washington graduate student who apparently applied here too as a graduate student. But sorry, he preferred the other UW. And that's Lucas Harris. And so Lucas is head of GFDL's weather W department, and they are the department that basically most exercises very high resolution models on global or very large regional scales. They have versions of their model which run globally, but they also have versions of their model that run over the Atlantic, the tropical Atlantic for tropical cyclone forecasting, for CONUS, for severe weather, and a couple of other regions as well. And also another group that's really been important in my explorations of very high resolution models has been a group of people at the University of Washington who are part of a PIRE group. It's an NSF group that supports international research and education. But ours was focused on cirrus clouds, in particular cirrus clouds in the uppermost troposphere in the tropics. So these clouds are created primarily by very deep convection, which then injects ice into the troposphere and occasionally even the lower stratosphere, and that ice spreads out and it evolves and it interacts radiatively to create other interesting cirrus clouds. But if you want to understand these clouds, it's very helpful to be able to understand the fundamental process that creates these clouds, which is convective updrafts lifting ice into the very uppermost atmosphere. And so to do that, you kind of need a model that actually simulates those kinds of clouds. And so the kind of model I'm talking about, global storm resolving models, in fact do that. So we use those models and compared them a lot with the data as part of this PIRE project. And then lastly, there are a couple people who've really been important pioneers in this field, and we'll introduce both of them a little bit later in the talk. Bjorn Stevens of the Max Planck Institute for Meteorology in Germany, and Masaki Sato at the University of Tokyo in Japan, who have played a very important leadership role in developing kilometer scale models of the atmosphere, and in fact even the couple atmosphere-ocean system. And in addition, I have two other colleagues, Peter Caldwell, who leads the effort at Lawrence Livermore Labs to create a kilometer scale model. Their model is called SCREAM. Anyhow, it actually holds the record for being the fastest model of its type in the world. I'll tell you how fast that is later in the talk. So he's really pushing the high performance computing constraints and limitations of these models. So I think his group is in perhaps best positioned of all the groups in the world to provide interesting results in the next few years from this type of model. And then Murat Karudinov, who I've worked with a lot in the past, and who worked with Dave Randall at Colorado State University a lot, who in the last decade did a lot, again, completely single-handedly to make very large-scale cloud-resolving models of interesting parts of the Earth's atmosphere that I and other people then work with Murat to try and help interpret. And so he's had a major role in pushing this field in this country. So, okay, so I'm going to return to a slide I had last night, which is the concept of, is a global storm resolving model, such as shown in the center here, with 3-kilometer horizontal resolution, 72 vertical layers, is it an adequate digital twin you know, to the actual Earth, as represented by, say, this Himawari satellite image on the right, as compared, for instance, to a conventional climate model with a much coarser resolution. And I should say, our current generation of weather forecast, global weather forecast models is approaching this scale. So ECMWF, for instance, has a 9-kilometer operational resolution and is hoping to move down to 4 kilometers. So in the realm of weather forecasting, this is very nearly an operational capability on global scales, and on regional scales, like over the continental US, we already run 3-kilometer models. So understanding the characteristics of models like this, and in particular, how well they represent physical phenomena like clouds, which are important for climate, as well as weather, is something that's actually quite timely right now. Okay, so let's talk a little bit about what I call the global storm resolving model. So this term was actually coined by Bjorn Stevens, and basically refers to fine grid global models with a grid spacing of less than 5 kilometers and at least 50 vertical levels spanning the atmosphere. And so with this, these models are able to represent at least more severe, more organized deep convection. This is a very important breakthrough, since the parameterization of deep convection is one of the most challenging aspects of weather and climate modeling, and we've never really come up with a particularly satisfying foundational view of how to do it. And so if you don't have to do it, you're basically saving hundreds of person years of future effort. So, you know, if we could somehow avoid doing cumulus parameterization, we would have many scientific minds able to devote themselves to something that's probably more valuable. So my own perspective on these models was actually very much motivated by what I just said, which is I've seen a heck of a lot of people waste a heck of a lot of time on making parameterizations of subgrid processes, ones that are not resolved by the grid of a climate model, but are really important. And convection is one of the premier examples of that. So if we could get away from that, it would not only, you know, make the scientific community more productive, but also we are also very well aware that something that you can resolve, even if you can't resolve it perfectly, you almost always can do a better job than parameterizing it. We have to be very humble about parameterizations of subgrid variability. They work, but they don't work well. And so whenever you can resolve something, you should. So that was why I looked at these models and said, okay, they've taken the problem that I consider to be the most challenging parameterization model problem in atmospheric modeling, which is cumulus parameterization, and actually, you know, sidestep that problem. So what do we get for that? Okay, so in addition to deep convection, the other problem they sidestep is these models are also sufficiently fine to resolve most important topography. So for instance, over regions like the Himalayas or the Rockies or the Andes, a 3-kilometer grid will resolve down to individual mountains. A 25 or 50-kilometer grid can see that there's mountains there, but deep valleys or very tall ridges really all get smoothed out. So again, the representation is better, and what that buys you is that you think about airflow over this very complex terrain, you capture most of the processes that create drag over mountain ranges much more completely with a 3-kilometer grid than with, say, a 50-kilometer grid. And so as a result, you don't have to parameterize those processes like the parameterizations we currently put into climate models, like so-called mountain blocking or orographic drag type parameterizations. The model can do that for you. So these two things are really big advantages. Then the other big advantage of this kind of model is that we actually have a lot of experience with smaller scale models of this, with this kind of grid spacing, so-called cloud resolving models, because we've run them for decades over limited regions of the ocean or the atmosphere as process models to try and understand processes that occur inside clouds, the organization of clouds, and so on. And also, we're quite experienced with comparing them with satellite observations on the same scale. So there's a lot of synergy there too. Okay, so why are we talking about global storm resolving models now? And the trite answer is because it's only now that we have the computing capability to do it. But in fact, that's not quite true. This particular field actually started 20 years ago in 2005 with the first published model called NICAM from Japan, which Masaki Sato, who I talked to, was heavily involved in developing. And so what allowed this model was, in fact, what at the time was, I think, the world's most powerful, at least openly known, supercomputer, which was the Japanese Earth simulator. So it was a very powerful computer because not only did it have all these vector processors, which at the time were the state of the art, but they had also invested a lot in interconnecting them with a very high-speed interconnect that allowed it to tackle very large problems very efficiently. So uniquely in the world, they were positioned to think about a model of the Earth on 3-kilometer resolution. So they actually started that. So this was the first simulation of the world. This one is actually an aquaplanet simulation, so on a water world, but with a 3.5-kilometer grid. And what's shown here is the is just a simulation of the outgoing long-wave radiation from the model. So where this is low, then, well, where this is high, these are the subtropics. You're seeing down to warm ocean surfaces. These speckly regions here, where you have low OLR, those are regions of resolved deep convection in the model. And you can see that the deep convection isn't just occurring randomly. Even in this aquaplanet, it's occurring in organized clumps. You can see the convection has lots of different scales. You can also see some filamenting of OLR here that's associated with interaction between mid-latitude fronts and the tropics. And you can already sort of see all the processes you'd like to see. So great, okay, this looks promising, and they quickly followed this with a real geography simulation of the Earth at similar resolution. But there were still some issues, and these are still the kinds of issues you have to keep in mind. So one thing that they did is they also ran this model, exact same model, at 7 and 14-kilometer resolution, which they could do much more cheaply. They could run it for longer, and then they compared the zonal mean precipitation distribution from these three model versions. Now, of course, at 14 kilometers, deep convective updrafts are not resolved, and so you don't really expect a model which assumes that all of the convection is on the resolved scale to work very well. But you might still hope that they have a somewhat similar climate. But if you look at the precipitation distribution, well, in the extratropics, where we have a lot of large-scale mid-latitude cyclones, models all do the same thing, but in the tropics, you can see that the 3.5-kilometer model has a much tighter peak of the ITCZ. And so that tells you that there is still some significant sensitivity to the grid resolution. And so it remains even right now an open question, what grid resolution do you have to get down to before that sensitivity goes away? We think 3 kilometers is probably pretty close, but looking at this plot, you could think otherwise too. So I guess the point is these models look cool, but whether they are quantitatively realistic, that's the really interesting question. So the Japanese group actually, for a long time, had this field to themselves. Their Earth simulator was still the best game in town, and other groups hadn't got around to creating a comparable model. And in fact, in 2013, they pushed this model to do simulations of the entire globe at less than 1 kilometer resolution. It could only do this for a day, but it was enough to make cool pictures. So this is like a 3-dimensional image of all of the individual convective clouds in one very, very teeny spot of their model off of Japan, which is like a zoom in of this region, which is a zoom in of this region, which is a zoom in of some little region in here. So, this model, just think about how much data this model is generating. The hardest part of dealing with this model is not running it, but it's actually analyzing the output. But they ended up exploring a number of interesting topics, including tropical convectively coupled waves, the MJO, climate sensitivity, although with very short simulations, so I'm not really sure the results were valid, even a little about aerosol cloud interaction, sensitivity to microphysics schemes. So there was no other model that had comparable characteristics until 2017. Basically, so that's when the rest of the world kind of caught up. And there were a number of groups that in the previous 5 years before that had been developing models of this kind. But by 2017, there were about 4 or 5 or 6 different groups that were ready to run models like this. And so that led, so before we get that, there was one little interlude that I wanted to make. Okay, but there were models that were not quite global, but still had some of the characteristics of global models. And one of the people who was really pushing this was Murat Kurutanov of Stony Brook University. And so I worked with Murat, and I like this picture just because it's cool from the fine art perspective. But basically, this is an example of a tropical channel aquaplanet. So here, you approximate the Earth as being like a Cartesian plane over the tropical region, and it's an aquaplanet simulation, and it goes from 30 degrees south to 60 degrees north, and this particular simulation was initialized with, or was forced with a sea surface temperature distribution, which had a maximum, I think, 15 degrees north of the equator, which is, and I think that's sort of somewhere around here in the middle of the domain. But again, the simulation had 4-kilometer resolution, so it was able to, again, simulate individual convective storms. So you can see some really cool multi-scale phenomena in this simulation that I've been advocating to Angel and Larissa and others. Oh yeah, you should look at this kind of model a little bit more, just because of the things that it does. So for instance, here you can see a very tight ITCZ here, and it has waves on it, and those waves end up spinning up into vortices, which turn into tropical cyclones, and then these tropical cyclones go and they recirculate into the mid-latitudes. It has then mid-latitude cold air intrusions, which then ultimately ventilate the tropics. It has like all of the phenomena that you would love to study in one model. And actually, this model is not that expensive to run either. So the point about this is there were other things going on, but nevertheless, in terms of realistic global modeling, 2017 was kind of a watershed. So at that time, Bjorn Stevens, who had been developing one of these other global storm resolving models, got together with Masaki and proposed an intercomparison project called DIAMOND. So DIAMOND is an acronym that I don't think I can actually tell you what it means. It's a cool acronym. There's dynamics, there's atmospheric modeling, there's other stuff in there. But in any case, the point of it was all the models that participated in DIAMOND, what they had to do was make a 40-day hindcast starting from ERA 5 initialization on a particular date in summer of 2016. They all were supposed to use specified sea surface temperatures. They were all supposed to crank away and see, well, did they agree or disagree? And 40 days was chosen, I think, for the biblical reason of Noah's flood, but it had it actually had the advantage of being a 10-day period where you actually expect these models to have forecast skill and to actually agree with each other, and then a 30-day period where they kind of get to choose their own climate to some extent. So you get to see kind of their weather and their climate skill at the same time. Now, I should point out that every single one of these produced a heck of a lot of output. 100 terabytes of output per GSRM. And one of the great achievements of this was actually that all of that output was put in one place, this German data center called DKRZ, and made available to a large group of people to analyze. There were full workshops where they were hacker workshops to analyze the data. And so I think this really got the idea of analyzing these models from a niche thing into something that people actually were doing. Now, this plot is kind of iconic of Diamond. So basically, I don't know how many of you know about this, but if you don't, so there are 9 models here, clouds from 9 models, and one of these is a satellite picture, and you can figure out which one it is. I won't tell you. We can go back at the end if you're interested. So if you looked at the previous picture, we'll go back there again just in case you're making your guess still. You can see that, okay, at first glance, all of these models kind of look the same. This is chosen, I think, only a few days into the simulation where the cloud patterns all kind of correspond still deterministically to similar weather patterns. But if you look in more detail, some of these models clearly have different cloud characteristics than others. And so that's the question. So that's the caveat emptor part of this. So let's go and take a look at that. To what extent are these models giving the same answer, which would be great, which would be robust, and to what extent are they giving different answers, which says that fine grids are not really the solution to this problem by themselves. So these are 3 of the models. This is the IFS model, which is actually the operational version, but which is, well, this is a research version of ECMWF's forecast model with 4-kilometer resolution. And what's shown here are islands off of Japan. I think this is supposed to be Mount Fuji here, because this was, Bjorn and Masaki Sato. Masaki Sato lived in Japan. And these are the clouds simulated by the model at this particular time. Here's another model. This is ICON's German model at 2.5-kilometer resolution. And here you can see, well, there's some very clear, like there's a cumulonimbus cloud, really nice looking. But the clouds have kind of a different character, a lot more convective clouds. And the topography is actually much better resolved. And that's not just the better resolution, that's actually simply by choice of how much the topography is smooth to avoid numerical artifacts. Here's another model, SAM, Murat's model, also 4-kilometer resolution. And here you can see the cloud, even the cirrus clouds, have a popcorny characteristic to them. So you look at this picture and you go, uh-oh, these models don't look quite so much like each other. So let's go and look at this theme a bit further. So one thing you might ask is, to what extent do these models produce the same precipitation distribution averaged over the 40 days? Because we would like them to have the same climatology, especially if we're going to rely on them as the machine learning basis for making climate models or climate emulators. And so these are the models, all of these different colors, and this is an estimate, an observational estimate, which probably should be treated with a grain of salt over the Southern Ocean. But anyhow, what you can see is that all of these models do actually track each other's precipitation climatology pretty well, even including in the tropics. They're not perfect, but they're not bad. If you were to take sort of 9 global climate models with 100-kilometer resolution, I think they would be pressed to agree with each other as well. And then you can ask, well, how well do they do in terms of precipitation intensity? So in this case, this is like a percentage versus precipitation intensity in millimeters per day in logarithmic bins. And here, each one of these pieces of spaghetti is one model, one GSRM. This is the average over all of those models. And then these are 2 observational estimates from the 40-day period of Diamond. And you can see, well, the PDF of these models varies quite a bit, and it's systematically a little biased away from the observations at moderate and light precipitation. It does capture the heavy precipitation tail pretty well, which is nice. So extreme events, these models seem to actually be doing an okay job on. And if you can compare that, let's skip over the middle one, which is intermediate models, with climate models with a grid that's bigger than 50 kilometers in grid spacing. And again, there's a bunch of spaghetti. And again, the models tend to overestimate mid-intensity precipitation. In this case, they slightly underestimate high-intensity precipitation. You can argue, in fact, the paper did, that this is better than this. I think that's a little bit in the eye of the beholder. I think in this case, you could say you've made some improvements, potentially, to the precipitation intensity simulation of the model, but they're not exactly overwhelming. So, okay. So there's good and there's not so good. That's kind of, in many ways, the moral of the entire presentation I'm going to give you. Here's another good case. So what we did is we, in order to do this, we had to do this simulation in a slightly kludgy way, but we took a diamond-like simulation with the GFDL entry into this horse race called X-Shield. And we took a 3-kilometer version of that model and we calculated its precipitation biases versus GPCP. Now, in order to take a 40-day simulation and compare it to GPCP, we actually had to cheat a little bit. And the way that we cheated is we actually, on very large scales, nudged the meteorology, the temperature and the wind fields of this model to reanalysis so that we kind of track the actual weather events that occurred. Then we did exactly the same thing with a 200-kilometer version of the same model. And so here, then, these are the biases with respect to the GPCP observational climatology. And the important point here is, of course, there's reds and blues in both cases, and reds are positive biases. Wetter than climatology, blue is negative, which is drier than climatology. But if you compare these colors versus these ones, these colors are much more intense. Particularly, they're much bigger biases over Central Africa and the Sahara, much bigger biases over the Himalayas, and also the Andes in this 200-kilometer model, which have, like, to a substantial extent, reduced or gone away in the 3-kilometer model. So for precipitation over land, this really seems to make a big positive improvement. Okay, well, now let's go back to the other story, which is tropical cyclogenesis. So a 3-kilometer model is now very well positioned to resolve tropical cyclones. So one of the great possibilities of global storm resolving models is maybe they can be a really nice way of understanding the global statistical characteristics of tropical cyclones, how it might change in the future climate. So then you can ask yourself, well, over the 40-day period of these diamond simulations, which models simulated tropical cyclogenesis? Did they simulate it in the right place? Did they simulate the right amount of it? And that's the plot on the left. So here are the observed tropical cyclone paths for the 40-day period. So there's some in the West Pacific, some in the East Pacific, a couple in the Atlantic. 24 total in this case over the 40-day period. And here are the different models in yellow. So, if you take a look at them, well, the good side is that they all are kind of producing tropical cyclones in the right place. And the characteristics used to say something is a tropical cyclone here, and then the observations are really the same. You still need hurricane force winds, et cetera. Each of these models is a little bit different. So, this model, for instance, is not producing much East-Pacific tropical cyclogenesis. But if you look at this plot, I guess I'd say, well, that's not too bad. All these models are kind of doing the same thing as the observations. That's good. The less happy side of the story comes if you look at the cyclone structure. So what's shown here is the most powerful cyclone at its deepest central pressure simulated over the 40 days for each of the models. And so here what's shown is wind speed. So basically 80 meter per second winds. That's pretty darn powerful tropical cyclone in this case. Is Sam, which is having some problems. And then you have like everything in between. So these other models, we have 4 or 5 models which are producing sort of reasonable looking tropical cyclones. IFS is having a little bit of trouble with the eye of the tropical cyclone in this particular case. But in any case, you can still see that even though all these models should be able to simulate a tropical cyclone, they're actually doing so a little bit differently. Okay, so another thing that we are really interested about these models is it seems like they're a very good way of exploring the global statistics of deep convection, right? Because these models can resolve deep convection. And we care about things like the strength of deep convective updrafts because they can produce, for instance, lightning, hail, flooding, etc. They may affect the depth of the troposphere and the height of the tropopause. So you can ask, for a few of these models, we actually have the information that we need to calculate the vertical velocity at some particular level and its histogram, both updrafts and downdrafts, and so this kind of tells us about the distribution of convective updrafts. This plot, I think, is not for all regions of the world. I think this is just for the I can't remember, it's either the West Pacific or the Sahel, but one particular region. But what's shown here then is the relative frequency of updrafts of different strengths. So this is basically no updraft or downdraft. These are weak downdrafts, all the way up to the strongest downdrafts of basically 15 meters per second, and all the way up to the strongest updrafts of up to 30 meters per second for the blue icon model. So all of these 4 models are all producing roughly the same PDF on this logarithmic scale, but if you look at the details, they are pretty different. So for instance, at the 10 to the minus 6 frequency, FE3 produces updrafts of 35 meters per second, while the NICAM model produces only 20 meters per second updrafts, which a little bit more than half as strong. So you could look at this plot as being good or bad, depending on who you are. It gives you a lot more information than a climate model would, but on the other hand, there still is some uncertainty there. We think that this uncertainty is probably due as much to the numerical formulation of these models as it is to the microphysical processes in these models. So another thing then is you can ask, well, okay, so what about the spatial organization of convection and the clouds it creates? So here what we can do is we can look over a 10 by 10 degree region of the Sahel, and over the 40-day period, again, that period was chosen with the highest mean precipitation over the Sahel region. What's shown here is the spatial structure of the precipitation rate in that 10-degree region from each global storm resolving model, and then the optical thickness of the ice, the frozen water path, how much ice is in the column. So basically, if you want the thickness of cirrus clouds in each of these models. So this is the convection, and this kind of tells you something about the anvil clouds that it's producing in the different models. So again, you see that the different models actually have some similarities and some differences. So all of these models are producing like squall line type convection, which is actually very characteristic of convection going across the Sahel, associated with often developing easterly waves. The characteristics are not the same, but they are vaguely similar. But if you take a look at the clouds they're creating, you can see some pretty big differences. So NICAM tends to fill the entire region with thin cirrus clouds, with kind of blurry edges. FE3 is much more localized, localizing the cirrus a lot more, probably associated with its microphysics scheme. And then SAM is trying to make, as I said, popcorn cirrus, which are actually associated with noise in its vertical velocity distribution that I think is a little bit of a numerical artifact. And icon has this funny fibrous characteristic to its anvil. So here again, you see, okay, so these models are feeling the effects of their different microphysics, ice microphysics schemes, which do some of this work, and also the dynamics. So they're all kind of making nice representations of the clouds that individually could seem fairly plausible, but they don't agree that well with each other. Okay, so let's go and talk about a couple of other interesting aspects of these models. So this one is from a paper about the SCREAM model that I was telling you about, which was kind of a late entrant to the global storm resolving model game. In general, we don't think of global storm resolving models as having a great chance of doing a great job with low clouds, because low clouds over the ocean and over the land are often sustained by quite small-scale turbulent or convective motions, you know, where the updrafts and downdrafts might be 100 meters or a few hundred meters across. That's not going to be resolved by a 2 to 5 kilometer grid. But nevertheless, there are some things that these models do kind of well, and they do well in a systematic way. And one of them is that when we look at satellite pictures of clouds over the oceans, low-lying clouds over the oceans, it's never that you see a uniform sheet of cloud. The cloud is always thicker in some places, it's thinner in other places, it's organized on the mesoscale. And this picture from Peter's paper that shows a simulation off the west coast of South America in one of the world's major subtropical stratocumulus regions of the cloud field. And now one could argue about why this is, but you can see that there's some grid scale structure, which might be the model trying to do convection on the 3 kilometer grid, even though the real convection is on a much smaller scale than that. But you can also see that just like patches which are brighter and patches which are less bright, and there's texture, mesoscale texture in the cloud field, which is actually quite realistic. And so that's another feature that these models do quite well. Cold air outbreaks, for instance, look quite realistic with these kinds of models, even though they're not really fully resolved by them. And not only does the horizontal structure of these clouds look right, but if you were to actually compare the vertical structure of the liquid water in these clouds averaged over this region with a satellite-based observational estimate based on a mixture of passive and active sensors, which is, I think, the C3M here, CCCM from NASA. You see the clouds are positioned in the right height of the atmosphere and have roughly the right vertical distribution. So actually, that's a very sort of positive, unexpected positive feature for these models. Okay, so lastly then what I want to do is say, okay, well, let's take a deep breath. We know these models sort of work, and maybe they sort of don't work, and they sort of agree and they sort of don't agree. Let's take a look at what these models say about future climate, since pretty much every grant proposal we have to write always has to say something about, well, and in the future climate it's going to do this, and that's why you should fund me. You're going to need to know this. Well, look, so we can ask some questions about future climates with these models that we can't as easily with other models. And also, I think these models have certain advantages for looking at unseen climates. So one advantage is that they avoid subgrid assumptions about clouds and convection, which can sometimes contaminate how sensitive a model is to climate, especially how sensitive the clouds in a model are to climate change. So by avoiding unnecessary assumptions about subgrid variability of cloud, they're sort of intrinsically better or more reliable models. However, as I pointed out, that only is true for some kinds of clouds, and marine boundary layer clouds are perhaps the single most important kind of cloud for affecting the sensitivity of the climate to changes in CO2. And these models are not intrinsically, inherently better for simulating that than regular climate models, even though they produce better mesoscale variability. And it's also the case that these models have, as we showed before, cirrus clouds which look pretty different from each other, and that's because they're relying on relatively uncertain ice microphysics parameterizations, which are important even at this grid resolution. So, okay, so, well, but let's just try it anyhow. So one thing that's interesting here has to do with cape and updraft strength. So one thing that that cloud resolving modeling community learned a while ago, and which I think people had suspected before, was that there's a fairly robust prediction from doing doubly periodic simulations on limited area domains over warm oceans, looking at the convection that develops, that if you have an ocean with a cold temperature, and you look at the vertical velocity, the extreme vertical velocities as a function of height through the cloud layer, through the convecting layer, which in this cold SST only goes up to about 250 hectopascals, you see relatively weak updrafts, and then as you juice up the sea surface temperature by 10 degrees, the strongest updrafts get noticeably strong. Now it's interesting, this is totally a feature of extreme updrafts. For the average updraft in all of these cases is actually only on the order of a meter per second in all of these rows. But the extreme updrafts get more extreme by far in a warmer climate. And in fact, that's associated with the fact that if you go to a warmer climate and you compare the temperature distribution, which is the solid lines, to moist adiabats, which are the dashed lines, and you take a look at the difference between them, which is the convective available potential energy, or CAPE, you can see the CAPE is massively expanding as you go toward a warmer climate. So the way you understand this is that the garden variety updrafts, they entrain as they go up. They can't take advantage of this CAPE. And as it gets warmer, the degree to which they can't take advantage of this CAPE increases because there's so much liquid in them that there's a lot of evaporative cooling that the updrafts can undergo that basically prevent them from ever getting very buoyant. But the strongest updrafts, which somehow, by hook or crook, entrain less air, they're able to take full advantage of this CAPE and basically end up in the upper troposphere going really fast. So, okay. So now, this is in doubly periodic simulations. What about in a global cloud resolving model simulation where we confront this with the real atmosphere in all of its glory? Does the same thing hold? Well, it turns out that in the one model where I know where we've tried this, it actually does show the same behavior. So 2-year simulations have been done with GFDLs, X-Shield, GSRM, in different climates. A control climate with present-day SSTs, the seasonal cycle thereof, a plus 4K climate where they're uniformly increased by 4K, a climate where only the CO2 is raised, a 4 times CO2 climate, and one where both is done. So overall, these are like 8 years of simulation with the GSRM, which is a lot of computing. So what do we see from these? Well, what we can see from these is 2 curves here. So let's just focus on the black curve and the blue curve. So black curve is the control climate. Blue curve is kind of like a future climate, more CO2, warmer. And we can compare them. So first we can start by looking at the temperature profiles. And here you can see, certainly it's the case that in a future climate, the tropopause gets deeper by about 1 kilometer. That's actually a very robust feature of climate models as well. If you look at the CAPE, which is not shown here, you would find that the CAPE is also increased. I'll show you a future picture in the warmer climate. Then we can look at, and another interesting feature here is we see some divergence here. If you add CO2 to the climate, you warm the troposphere, but you actually cool the stratosphere. So if you add CO2 to a 4 plus 4K climate, suddenly the stratosphere gets colder. That's actually something we've really observed too, as you learned about in your radiant transfer class. But okay, so now let's take a look at the effect on the updraft strength. So this is a PDF of maximum updraft strength over the entire domain. And so here's the control climate, and here's the warm climate. And you can see the frequency of, say, 50 meter per second updrafts. The control climate is the same as the frequency of 60 meter per second updrafts in the warmer climate. So basically, you've got about a 15 or 20% increase in the peak updraft strength. So there's a very robust prediction here that a warmer climate is going to result in stronger convection, probably more lightning, definitely more convective overshoot of its neutral buoyancy, etc. And this is the picture of Cape from this model. So this is Cape in the control climate. It's averaged around the entire day, which is why you don't see much Cape over land. But you can see Cape values going up to maybe 1,000 or so joules per kilogram on average over the tropical oceans in this model. And this is then the change in Cape in the warmer climate. And you can see a whole bunch of red, which is an increase in Cape. What's impressive is just the magnitude of this increase. So we're getting increases in Cape by something like 400 joules per kilogram, so 30–40%. So even with a modest climate change, such that we might even reach there by the end of the century if we don't get our act together in terms of emissions controls, produces very large changes in Cape and pretty substantial changes in extreme convection. And this type of model is really good at telling us about that. So lastly, I wanted to talk about cloud changes. So we can also ask about, well, how do clouds change in a warmer climate, and do these models agree with conventional climate models? And cloud changes are important because cloud feedbacks on climate change are one of the most important uncertainties in how fast climate will warm over the long term, and how much it will warm for a given amount of greenhouse gas concentration. So here what we can do is we can look at the distribution, say from a GSRM, X shield in this case, of cloud cover as a function of latitude from the South Pole to the North Pole, and height through the depth of the troposphere and into the stratosphere. So you can see a lot of clouds toward the poles, less in most of the tropics except near the tropical tropopause. And then you can ask, well, what happens if you warm and you CO2ify the simulation? Where does the cloud increase and where does it decrease? And you can see that there's then decreases in cloud here, increases in cloud here. And then you can compare that to the changes you see across an average of CMIP conventional climate models. And now the caveat here is that the color shading is reversed. So here red is positive and here red is negative. And the latitude scale is different. So this one, latitude is uniform, and here it has an area-weighted scaling. So it's a little hard to bend your eyes around what's happening. But to some extent, this red corresponds to that blue. This blue corresponds to this red. This red up here corresponds to this blue here. You can actually pattern match the features, and if I had both of these plotted on exactly the same scale, it would look more convincing. But the point about this is that actually the cloud changes you see in the GSRM are actually quite comparable to the ones that we see in conventional climate models. And we could quantify that in terms of cloud feedbacks. I think in the interest of time, I'm not going to do that. I'll skip over the slide. But basically, what it shows you is that if you compare the climate sensitivity of this model, which is a result of mainly of cloud feedbacks, star here, to a range of conventional models, that it's actually within that range. So we don't find some nasty surprise about cloud feedbacks from looking at GSRMs, at least not this one. Okay, so that brings me to the conclusion. So basically, I wanted to talk about, what are the pros and cons? Well, more trustworthy spatial detail over land, probably more defensible extreme precipitation. We have an internally consistent treatment of clouds, precipitation, convection. There's a strong connection with weather forecast models, which now work on this scale as well. And then even with only a few of these models, they're kind of like an alternative perspective on climate change to CMIP. So they can kind of test the robustness of CMIP climate projections. Are they worth their conventional expense? Well, their huge expense? Well, that kind of depends. Mainly, the huge expense means that you can't afford to do very many runs. So you have to be clever about how you're going to tune these models to be realistic. Basically using tuning on weather timescales rather than climate timescales. And also you have to make sure that if you do a run like this, that many people use it. So I've been trying to advocate, even here at University of Wisconsin, that if you guys think these results are neat and you can think of any ways to use them, let GFDL know, let other modeling centers know, let me know, and I can try and help put you in touch with the people who actually can tell you how to get at the data, and I think everyone would be excited to see more analysis of what these models are good and what they're not good at. I will say though that just like with machine learning not replacing climate models, these models are not going to replace 25 to 100 kilometer GCMs anytime soon too, just because they're too expensive to run. So they're just one tool in the arsenal. So anyhow, so that's kind of my take on GSRMs. I'll be happy to take any questions. Yes?
Yeah, thanks, very cool talk. Thinking back to your precipitation rate plots, comparing back to the satellite products, we know there are uncertainties with satellite products of precipitation. Is there a thought that maybe these models might get more of the truth than what the satellites are actually seeing?
Yeah, so that's a really good question, especially over the mountains.
Yeah.
Because over the mountains, you can't really use microwave. Trim is kind of pretty dubious in terms of surface precipitation or GPM. So yeah, it's possible, but I think we'll have to do a pretty careful job of analysis. There's some places, like for instance in Switzerland, where there's actually a fairly dense network of gauges. And in the western United States, we have things like snow-tell sites, which are somewhat absolute measures of at least time-integrated precipitation. So I think there are opportunities for testing that, but I'm not really aware of, I'm not plugged into that field well enough to tell you, what level of data is actually available for this right now that the climate model could really use. Yeah.
Yeah, Chris, really interesting. It shows that these models can, when looking at individual elements, they're comparable though not exactly similar between the different models, which is interesting in and of itself. What about interactions between the features that develop in these models? I mean, you spend a lot of time thinking about how the clouds look, how the precipitation on average looks. What about the effect that these precipitation features may have on the PV at the tropopause or the tropopause height, and then interactions that occur in the developments at mid-latitudes and the subtropics? Is that maybe the next step that a person could use these data to interrogate?
I think that would be a perfect use of these models, because to answer the questions like that and to kind of ground sort of theoretical ideas you might have, I think it's useful to have a model that has all of those things represented in some degree of plausibility. And maybe they're not perfect, but in many ways their interactions are probably much more perfectly represented here than if you didn't resolve a lot of the details. And so I feel like, there's all kinds of potential for using models like this to study very complex phenomena, latent heating in extratropical cyclones or whatever, or extratropical tropical interactions, all those kinds of messy problems. These models don't give you insight by themselves. You still have to analyze them. You have to compute PV fields or heating or whatever from what you've got. But on the other hand, I think they can think through those interactions so much better than the person can that you'd be a fool not to use them. Yeah.
Great talk. I was interested in a broad comment you made and just sort of hinted at the sensitivity to the numerical procedures it was different for different models. And that's meant that there a lot of the smaller scale details would have presumably been really off due to different time and space differentiation.
Right, yeah, exactly. So like, for instance, for that global SAM model, it has basically grid scale noise in the vertical velocity field of about 1 meter per second that I'm convinced has to do with the fact that it uses a Poisson solver, a global Poisson solver, to calculate the pressure distribution. And the global Poisson solver is an iterative solver, and I don't think it was run convergence. And so it still had errors in it, and that's actually creating the speckle. What's ironic about that speckle, though, is that if you take a look at, for instance, at observations of vertical velocity at the tropopause, which are, I think, mainly associated with gravity waves, propagating gravity waves generated by underlying convection, it turns out that SAM is the only one of the models that produces the right level of variability of vertical velocity at the tropopause. The other models are all way too weak. So in some sense, the noisiness you see there, it probably doesn't have the right pattern, but it actually has the right amplitude to be realistic. And so in this case, you know, a bad model can sometimes serendipitously give you, for some purposes, a good result. But yes, especially for convective updrafts, if you think about an updraft that's a 1 grid point across or 2 grid points across, numerics is, you know, totally the name of the game in terms of how much that is damped by neighboring downdrafts or regions of non-updraft there. Totally depends on the numerical method you use. And so if you ran all these models at 1 kilometer resolution, it would be interesting to know whether they would get any more similar. A hopeful numerical analyst would say yes, and a cynic like me would say, well, probably all the circulation would just collapse to the new grid scale, and they'd still look as different from each other as they are right now, but we don't really know.
So I was wondering, you had that PDF of updraft velocities that you showed, and I was wondering if these models tend to output snapshots that you have to calculate those from, or if there's...
Yeah, so basically...
PDF, yeah.
Yeah, so this PDF was calculated by my graduate student at University of Washington. The way that she ended up having to do it was download a region of 3D data that was sort of 10 degrees of latitude by 10 degrees of longitude, which she could, actually analyze in full 3-dimensional glory, and then get the vertical velocity at 14 kilometers from all of those models. But yeah, it's based on snapshots and a limited region. Ideally, your model
and you
would...
haven't done this for land versus the ocean.
Well, we've actually done this for an ocean region and for a land region, and you do see some differences of the expected type, although not as big as you might think. But the thing you see more is that regardless of whether it's land or ocean, the characteristics of the different models are the same. FE3 produces also the strongest updrafts ever land as well as ever ocean and so on. So you see the differences between the models persisting regardless of the convective environment.
Mm-hmm.
Yeah.
I'm wondering about using the use of some of these in training other ways of doing parameterizations. You comment that you want to resolve everything, but the way we've been going at parameterizations is sort of top down. And what about using these for training machine learning techniques for replacing parameterization?
Yeah, so you could do that. So for instance, you could imagine training an orographic drag parameterization, for instance, because if you take a look at those parameterizations, they're based on all kinds of very hokey idealized assumptions, which have been very much empirically tuned to kind of work. So there's a lot of, there's a lot of possibility for using the models that way. Again, I think just like with using regular GCMs, especially given what I said, don't just use one model to base your fine resolution model to base your parameterization on. Use a couple of models and see how different they are and see how much you believe the results before you get too confident in it. But yeah, I think there's all kinds of possibilities there. Again, it's all about people's imagination and different needs. I mean, one thing to say though is that, for instance, when we make year-long or multi-year integrations with GFDL's X-Shield model, the number of variables we store in full 3-dimensional resolution is 0. We store three-dimensional fields at the surface and top of the atmosphere, and we store two-dimensional fields at the surface and the top of the atmosphere. And the only three-dimensional data is stored coarse into a 25-kilometer grid. This is the only way you can actually store the data on the computer that we were running it on. So in order to do three-dimensional native grid resolution analyses, you actually have to have decided beforehand that you're going to do that and customize the simulation to make that possible. So this is where there has to be a bit of a conversation between the model runners and the model users in order to make these models as useful as possible. Yeah.
I know these are already computationally intensive and data intensive, but is there, probably don't include very much atmospheric chemistry, very much aerosols,
Yeah, right.
sorts of processes. Are any of those important in getting the right answer?
Yeah, okay, so it kind of depends on what the question is, right? So, one thing is, so if you're, okay, forgive me because I will sin, but I work with a lot of atmospheric chemists and I work with a lot of aerosol physicists, and they are all convinced that their field is the most important climate process that exists. And if you ask the right question, they're correct. But if you ask the question of generally, okay, how does the weather evolve, or even what is the climate sensitive to, that's not really correct. Especially it's not true in the weather. ECMWF, for instance, they have an aerosol scheme. It has some slight impact on their radiation parameterizations. It doesn't, I think, have any impact currently on the microphysics scheme. And they make the best weather forecast in the world. So, it's one of those things where it only matters if you're interested, say, in the aerosol direct and indirect effects on climate or 20th century climate change, then of course aerosols matter a lot, and you have to include those processes.
Well, and on the microphysics as well.
And the microphysics too. But for instance, you can go a long way, and in fact these models go a long way by just assuming the droplet concentration of liquid clouds is 50 per cc over the oceans and 200 per cc over land. You can hardly tell the difference with doing something better. So I think it really depends on the question you're asking, and so always when you load a model up with chemistry and aerosols, you'll have to take other computational hits, and there are some problems for which that's appropriate and some for which it's not.
And you mentioned that the cirrus cloud microphysics might be the low-hanging fruit to try to improve upon.
Well, we think that that's something which can change the behavior of these models fairly significantly, and not just for climate change, but even for things like the MJO, where any place where there's a lot of interaction between OLR and circulations. So OLR is quite a positive feedback in many cases on many tropical organized convective circulations, and so getting that right is important. And tropical cirrus clouds, they're thin, but they cover a lot of ground, and so they can be quite important for OLR. I think, yes, that is probably low-hanging fruit. But it's also hard to study, and there's a lot more fundamental uncertainty about what the right thing to do is. So, it's low-hanging, but it's not. It's not like you can just pick it. Yeah. Okay, great.
Okay, let's thank Chris. If you have more questions, you're welcome to come up and ask right now. I believe he doesn't have any meetings on your schedule.